Online Academy binder systems for additive manufacturing of sand cores with binder jetting. The speaker for today is Dr. Dominik Polzakiewicz, Specialist 3D Printing. My name is Dr. Christian Appelt and I will guide you through today's webinar.
Thank you very much, Christian. And also from my side, a warm welcome to the webinar today. Let's jump right into the agenda. First of all, I would like to take a few minutes to talk about binder jetting technology, which is the predominant process of additively manufacturing sand cores. Afterwards, I would like to join into some more specifics about our ASK binder systems for 3D printing, which are Ascuran 3D, Novaset RP, and Innotech 3D. And I would like to close the webinar with some concluding remarks. Let's take a look at binder technology itself. So many of you may already know the process of binder jetting or additively manufacturing coming from a 3D model on the computer, which is then sliced into two-dimensional images. A thin layer of molding material, typically thicknesses of around 300 microns, is spread out in a building platform and afterwards selectively printed with binder according to the 2D data generated. The platform is then lowered and the step of spreading a layer and printing an image is repeated until the job is completely finished. After the finishing printing, the remaining loose material which was not printed has to be removed from the printed parts, and we obtain the finished component. With this technology comes some advantages. Of course, one very prominent one would be the possibility to create very complex geometries or even designs which were thought of being impossible to manufacture. This also includes integrating parts into each other, so printing parts that have to be assembled afterwards, print them already in one part in the process. Of course, the digital nature of the process enables for very flexible production, therefore leading to shorter lead times in production. Combination with conventional parts is possible, so that not everything in a core package has to be printed. It can be combined with conventionally manufactured parts. But besides advantages, there are also some challenges that have to be met. So it's a rather new technology. So growing pains will be inedible at some point. Productivity is still quite low, especially compared to high throughput conventional applications, but is steadily increasing. From a price standpoint, printed cores are still more expensive than conventional fabricated ones, so this has to be taken into account as well. And the process is not only about printing. After printing, the parts have to be finished, which nowadays requires manual labor. So this has to be taken into account as well. Now, let's look at the material side of the process. So what is actually needed for binder jetting of sand cores? So let's start with the binder, which actually the main requirement for the binder is to be printable, to produce good, reproducible, and stable droplets out of the print heads. There are 5 aspects of the binder that, in my opinion, have to be fulfilled to generate this stable and satisfactory drop formation. This, for one, would be printability, which can be described as a combination of physical properties like viscosity, surface tension, or density. Compatibility, which refers to the binder being compatible with the printing equipment, so that there are no degradations over time or no harmful reactions between binder and printing equipment. Quality is very much important because we have very small nozzles we have to go through. So the binder printed or the printing ink has to be free of any particles which could clog the nozzles, for example, or any impurities that could hinder the printing process. Stability refers to the inks or the binders being very much stable in the printhead and not changing properties, so that printing, even after short periods of inactivity, still is ensured. And last but not least, there is a need for functionality. So we're not looking to print an image, we're looking to print a sand core. So from the chemical point of view, of course, the printing ink has to be able to provide a sand core which can be casted afterwards. Looking at the molding material that can be used, starting in the bottom left of the sheet, the sand is mostly very fine sand in terms of casting or coarse sand. So we're talking an average particle size of about 150 microns. Usually, as a rule of thumb, you could say it should not exceed half of the layer thickness to be really usable in printing. It is optimized for packing, since there is no or very few active compaction of the material. It has to pack itself very well to increase density. And we need a good flowability because it is spread out in thin layers. So we have to ensure that this spreading is always functioning well. Besides the sand itself, there are additives used in 3D printing. For one, liquid additives. One category of them would be hardeners in organic 3D printing, acting as a reaction partner for the binder. Adding liquids to the sand reduces the flowability, so there is a limit for those additives which can be added. And since they can be volatile liquids, one has to monitor the amount of liquid additives, especially when considering using not printed material and recycling it for the next printing step, printing job. A second category of liquid additives can be used to control binder migration after printing. So when the binder is printed onto the sand, those additives can be used to control the spreading of the binder in the sand layer, which can lead to optimized precision in the printed parts. The last category of additives which can be used are powder additives. They provide strength and thermal stability in inorganic 3D printing, but in general can also promote flowability in the molding mixture, which is, as mentioned, very important for constantly being able to spread the layers in the building platform. Given the right particle size and compatibility, also casting additives are possible to being added into the molding mixture already. So let's have a more detailed look into the printing systems provided by ASK. And let's start with Escuran 3D, which is a furane binding system combined with a liquid activator in the sand. So in terms of the molding mixture, most sand types are applicable with this system. And as already mentioned, there is a liquid hardener which can vary in type, and the variation in type already gives one the possibility to steer the process in terms of reactivity. So on the left side, you can see a graph which shows the hardening speed of different systems where the activator is actually used to adjust the reactivity of the system and therefore adjust the process times necessary. The binder consumption in Escuran 3D printing is around 2% or even less, and there is no necessity for post-processing the cores. So after taking them out of the printing box and finishing them, they are ready to use and have already gained their final strength. The final strength can be around 300 Newton per square centimeters, depending on the binder consumption. But for Ascoran 3D of urane printed parts, there is the necessity for finishing the parts. So there are sand adhesions at the parts which have to be removed mechanically. This effect can also be steered by using suitable activators. So the image on the lower left shows two different activators and a sample which was then descended simply by vibration. And one can see that using either activator A or B, a very different appearance of sand adhesions can be obtained, but it also comes at the price, in this case, with reduced strength. So there has to be a balance, which, by choosing the right activator can also be suitably selected. In terms of casting, a wide alloy range can be cast with the Ascoran 3D system. And if necessary, coatings are also obtainable from ASK. In this case, a very popular solution would be a water-based coating, the Solitec RP701. We also want to develop this system even further, and in further development, we're focusing on reducing the risk or the footprint in the working environment, so eliminating more and more dangerous components from the binder formulation, but also increasing efficiency so that remaining the same strength, binder consumption can even be lowered. And as already mentioned previously, improving the finishing with new binder formulations and new hardener formulations so that this becomes less and less intensive. And last but not least, we want to avoid the toxic labeling of the binder altogether by adapting ASK's MagnaSet technology for 3D printing in the future. Let's look at the phenolic binder system NovaSet RP, which is also combined with a liquid activator in the sand. And here the predominant sand systems are silica sand or synthetic or ceramic sand, and the liquid hardener is integrated into the sand. Binder consumption is a little bit higher, around 4%. And in contrast to Ascoran RP 3D, there is a necessity for hot air curing after finishing the parts to gain final strength. The final strength obtainable is very high. It can go up to 700 Newton per square centimeters. And of course, as the graph on the left shows you, is very much dependent on the binder consumption. So there is the possibility to adjust your strength level to your need by adjusting printing parameters. In contrast to Ascoran 3D, NovaSet RP has very easy finishing. So there is no need for extensive mechanical finishing of the cores. And the cores, after curing, provide a very high thermal stability in casting. As for casting properties, there are very good surface qualities that can be obtained with this system. And since it doesn't contain any sulfur or nitrogen, it's very suitable for steel or ductile iron castings. And we also can, provide coating solutions for this system as well, which can be alcohol-based, like the Velvacoat RP701, or water-based, like as the Solitec RP701. For this system, there are also future developments we want to attack, and this would be increasing the binder shelf life. It is not infinite, so we are working on increasing it even more to enable better and stabler handling over time. Some parts have to, depending on the geometry, have the tendency to show some brittleness. during handling after curing. So we want to address this to make it even more approachable in terms of assembly and handling and transport. And of course, process cost optimization is something we are looking into. This refers especially to recycling the sand and even reclaiming it. So there is a more cost efficient ways to produce, of course, with this system. The third system I would like to introduce is the Inutec 3D. So this is an inorganic binder system, which is not combined with a liquid activator, but with a powder promoter. The molding mixture, very similar to Novaset 3, RP, is mostly silica, sand, but also ceramic sands can be used. And the powder promoter has to be incorporated into the sand as well. And liquid additive is optional for this system, but it doesn't function as a hardener. It functions as an optimizer for binder migration. So what does this additive actually do? This diagram shows you the dimensional deviation of parts printed. That means that according to CAD data, there is a certain dimension we want to achieve, but due to what is referred to as bleeding, parts tend to get bigger than they actually should be. But with this liquid additive added into it, this deviation from the desired geometry can very much be controlled. The binder consumption for this system is somewhere around 3%. And similar to Novaset RP, there is a need for curing after printing. This can be done by hot air or, which is more popular, done by microwave heating. The strength levels of Inutec 3D are around 400 Newton per square centimeter. And like Novaset RP, the parts are very easy to finish. In regard to casting, this system is mostly suited for aluminum casting, and it provides the great benefit of no to very low emissions in the casting process. One ASK exclusive feature that this system contains is the adjustable thermal stability. So maybe this little experiment illustrates it best. Those are simple testing bars which are put on 2 anchor points and then placed in an oven at 650 degrees C. So without adjusting the thermal stability, after a period of time, the test bars will bend under their own weight. By adjusting the thermal stability, this behavior can be compensated for, and therefore the samples remain stable. In terms of coating, mostly there are no coatings used in this kind of application. Looking into the future for Inutec 3D, we want to further optimize the already mentioned sand binder interaction with those liquid additives to provide even more dimensional accuracy in the process. We want to increase or optimize the productivity. That means that the binder print head doesn't have to be cleaned that often during the process. Cleaning always means a loss of time, and therefore printers with less need for cleaning would be even more suitable to increase productivity. And of course, adjusting to customer needs. So we want to be able to offer tailored thermal properties of the cores so that each customer applicant can use their binder system for their specific casting process. Before I get to the concluding remarks, let me put in a few words in regard to special coatings for 3D binder systems. So we offer the already mentioned 3 coatings, which are either zircon-free coatings or zircon-based coatings, whereas zircon-free coatings can be obtained in water-based or in alcohol-based formulations, and the zircon-based coating is available in alcohol-based formulation. Those coatings are specially adjusted to the, for one, the fine sand used in the 3D printing process, and as well in their impregnating characteristics, so that some appearing roughness on the cores, since they are not molded in a tool, there is some inherent roughness to the cores, can be compensated for. So adjusting the particle size as well as the solid content in those special coatings allows us to tailor them for this specific material system, the 3D printing material. So let me conclude with some remarks in terms what we want to offer our customers. In terms of availability, of course, solutions for all 3D printing applications that are out there. And we want to also be able to keep up with developing printhead concepts, so that we are able to provide binders for new generational printheads, which are to come in the future. And one aspect we are focusing on is building up a worldwide portfolio. So it doesn't matter where you print your parts, you always obtain the same quality product for printing in each region. In terms of variety, the printed cores can cover a very large alloy range. And as already mentioned in the beginning, they can be combined with conventional produced cores. So there is no need to exclusively print whole part packages, but they can be combined. And of course, we are looking at constantly developing or further improving our binder systems to meet new or increased requirements for the sand cores. In terms of productivity, this is more something that is to be looked at from the machine side, but the machines are scalable, are stackable. So there is a possibility to start out small and then increase capacities. The degree of automation is steadily increasing, so there is a possibility to increase productivity even further, and aggregates for pre-processing like mixing sand with activator or post-processing like hot air curing or microwave curing are already available. So this is something that also increases, I think, the attractivity of the system.